Hi, my name is Victor. I am from the German Research Center for Artificial Intelligence, and today I am going to present you our research made in the context of the project METIS2, where we are investigating deep learning models for auto-completion of spatial configurations using semantic building fingerprint graphs. Our current goal is to find the most optimal representation of semantic features of the building fingerprint graphs, and we came up with the idea to use the data structure called relation map, which is a tensor, or more exactly the adjacency matrix of the spatial configuration graph. Each row in this matrix represents a particular room and its outgoing connection to the other rooms. And in order to represent this information, we use the numerical label topology, where we use specific numbers for the room and connection types found in the spatial configuration graph. In our previous research, we introduced three different types of the relation map. First one is the one-hot encoded relation map, which uses the one-hot vectors for representation of the semantic information found in the spatial configuration graph. The next one is the textual relation map, which uses the textual representation of the relevant semantic information. And the last one is a multi-layer relation map, which uses three layers for source, target, and connection separately in order to represent the semantics found in the graph. We evaluated these three relation map types using the specific deep learning models developed specifically for them, and we applied a classification task to this deep learning models, and we wanted to know how these models classify the spatial configurations from the training dataset. And in this first evaluation, the one-hot encoded map revealed itself as the best one in this comparison. It had the best classification rates, the highest classification rates, and it has the overall the most stable performance. Additionally, we also recorded that the all models are able to recognize the relevant semantic features in the spatial configuration graphs, and these results were published and presented at the conference Cadrea 2021. You can find the link to the paper in the description of this video. In the evaluation that we present in this paper, we wanted to dig deeper and wanted to know how the trained relation map models would react to the room configuration not available in the training dataset, which means we wanted to use the spatial configuration totally unknown to the models and measure the classification rate for these configurations. We reused the same deep learning models, so we did not retrain them or reconfigure them. And we measured again the prediction quality, which means the higher classification rate is, the higher is the prediction quality of the deep learning model. Also, we wanted to investigate for prediction patterns, for example, if certain models increase or decrease their classification rates depending on the grade of the modification of the unknown spatial configuration, and we want to then reconstruct the failure or success of the classification rate. So in the first phase, we used 12 manually created spatial configuration graphs based on existing buildings and fed them directly into the deep learning models in order to record the prediction quality. The results revealed once again that the one-hot encoded map has the best results of all. When we consider three results, the first three results, and search for the correct label within these three results, the one-hot encoded map has the highest rate of the almost 92%. In the second phase, we wanted to reconstruct this classification values and wanted to know if the one-hot encoded map, for example, has a stable performance, so if it always had the highest classification rate on the unknown spatial configurations, or if there are some situations where the classification rate might be worse or very bad. So for this we define two separate evaluation paths. One of them is the subsumed path, where we defined four different steps, and in each of the step we took the separate dataset, which is a further development of the previous dataset, which means we modified, for example, the dataset from the step 2 in order to get the dataset for the step 3. For the separated path, it was a little bit different. We performed all of the modification on the original dataset, and all of the modifications were then as well fed into the deep learning models in order to predict the classification to measure the prediction quality. The most interesting case here is the step 4 for both phases. Here we broke the class label, which means we changed the modification in the way that the class label was changed as well. And the results show again the stable performance of the one-hot encoded map, at least if we search for the correct label within the first 3 results, for the separated path as well as for the substitute path. Generally, we can say that the models react similarly to the changes to the training data, and the stronger the modification of the original graph is, the lower is the rate of the correctly predicted classes, except for one-hot encoded map, which again provides the best performance. And the thing that we notice it also is that if we break the class label, it provides the highest influence on the prediction quality, which means it's highly probable that the features that we defined for the class label, that we consider as class defining for the label, are not the feature that the model consider to make up the classification decision. However, this once again confirms that models are able to recognize the relevant semantic features, and this we can consider as the success of our research. I thank you for your attention, and if you have questions, you can contact me under the following email address.